Hello everyone, my name is Mohamed Issa and I am from Libya. I came here to do my PhD studies and I am presenting today the collaboration work of multiple people actually. One of them is June, which was a post-PhD at the University of Colorado, Denver, where I am studying at this moment. And the second person is Professor Yale, which has happened to be my PhD supervisor. And the third person is Lexi. I have not had the pleasure of meeting that person. And the last person is me, is Mohamed Issa. Thank you. To give you a broad understanding for this research which has been published, it's about a bridge. It's a historical bridge, an important bridge of the cultural heritage of Colorado. It's a 102-year-old Truss bridge. So it's more than a really old bridge to care about. So what they did is actually based this study on someone who did the research in 2014. His name is Dr. Truss, who's still a professor in my university, the University of Colorado, Denver. And he did collect the data and did the experimental work. And afterwards, they did base this paper on his research. So this research combines actually experimental work with other factors such as the machine learning and also modeling. So there are many factors which is important and involved in this bridge. So the bridge is being subjected to wind loads, and wind loads, of course, are an important factor for every bridge because they're very sensitive, especially for an old bridge, because there are a lot of degradation in the stiffness and also structural resistance of this bridge. So I will be explaining to you about the contents of this presentation, which I divided into 4 sections. The first one is a small introduction, and the second one is for the experimental program that Dr. Truss has prepared. And the third one is about the modeling process with the finite element modeling. And the fourth one is about the results, which have been combined. So a brief introduction about the history of the codes which has been used in this study. An ancient code which is very important, it's the ANSI A58.1 to ASCE 7 in 2016, which has been a really helpful resource for this study. And then afterwards, this one has been developed to AASHTO LRFD. And afterwards, for the ASCE 7, divided the importance of categories and the risk factors to 4 different categories. But this is not the most important one because, as I told you, this is a very important bridge and a very important cultural heritage for Colorado. And after modeling and using also machine learning to make it very easy for us to make it feasible. So after doing that and combining all of the resources and predicting the response of the historical bridge, there are very good results, which has been the result of using the machine learning, and very few errors which has been appearing after completing this research. So the accuracy of using the machine learning process was 0.67 to 0.95, which is a high factor which has been achieved. Moving on to the experimental program. So the steel bridge is 36 meters long by 5 meters wide and 6 meters tall. And it's a steel channel bridge with an eye bars and hot roll cables. This steel bridge has attached to it a sail to catch the wind-related responses, which has been used in multiple steps in this research. And then afterwards, multiple anemometers have been attached to the steel bridge to catch the response of the steel bridge, which are very important. And also 8 string transducers, 8 string gauges to measure some really important data points. So by the end of the by the end of this, not lab work, it's a field work, 1,104 data points were collected, and then they were used to make the random forest machine modeling and 3D finite element models. So that one made a full-scale testing which captured authentic boundary conditions. Unlike other ways to model real bridges, this is the most effective one, as we found out, because other ways will have to be involving wind tunnels and very expensive ways to achieve it. So on the left side of this slide, you can see the bridge, and at the lower side, the modeling part of this bridge with the associated dimensions. So moving on to the experimental program second half, which is the wind-induced force from strain to axial load. We need to transform strains to axial load. And how do we do that? We do that through this equation, Ft1 EA, the sum of strains over 2. And that will give us axial strains Ft1 and Ft2, which are shown in the left side of the slide and explained to be A and B. And by the end of that, we have to also calculate the wind pressure, which is a very important factor for this study. So the pressure was measured by this equation, P equals half of PV squared, rho V squared, where rho is the 1.225 kilograms per cubic meters, and V is the wind velocity measured in meters per second. For the truss members, there are very important equation which has also been used. P is 0.613 CD multiplied by V squared. So CD is also a very important factor, has been used, and the V also the speed of the wind. Moving on to the characterized wind speed, which has been obtained by the field work. There are multiple factors which has been used and modeled throughout the entire process of doing this research. And this equation also one of the most important ones in this research. So this equation has been used to also make the finite element and also the machine learning process by employing Python code to make the machine modeling part, and also using the data from the different strain gauges, the 5 strain gauges actually which were mounted in the bridge. On the left side of that slide, you can see some data which has been collected from the different calibrated sensors, the 5 of them, which has been developing different results depending on the location and the height of that sensor. So by completing this process, there were a lot of data which were collected. It's a range of realistic wind intensities from low probability to extreme probability, which is highly unlikely to happen in this case, which is 99%. But the most common level of winds is only 20%. But by the end of doing the research, we found out that only the range is between 40 to 60% was actually the realistic and common numbers. So by moving on to the modeling part and combining that with the random forest machine learning, there are multiple steps in achieving this, and one of them, actually the most important one, is doing the learning tree, which is a very important one. So for this research, 500 learning trees were made, and which later combined and then afterwards made the whole data set, which has been used to train and also validate the model. So, but there is one little off reading which was expected to be near the WS3, the strain gauge number 3, which was likely due to maybe some failure in mounting or maybe some failure in wiring. So that was the only one which it didn't give like a consistent reading with the other strain gauges. So jumping to the modeling and comparing that with the finite element analysis, by doing the modeling the wind part, so there are two different models which has been used, and one of them with the quadratic wind distribution and also the uniform wind distribution. So the quadratic wind distribution, which is commonly known as the Weibull fitted distribution, which really important one. But by the end of doing the modeling part, we found out that the most common and most effective way is a uniform wind distribution, which gave the most realistic results, and also when comparing to different ways of modeling, they give really low error results. But going back to the wind pressures which are necessary to model this bridge, one important factor is the pressure, which was calculated using this equation that you see in the slide. P equals 0.613 CD V squared. So CD is a shape-dependent drag coefficient, and it had two different numbers. The one of them is for the 2, and the second one is 1.7. One is for the shape, and the other for So by combining different boundary conditions, which has been tested on the left side, the lower left side of the screen, the most convenient one and the most one that gave realistic results is the boundary condition number 5. So B5, which combined the roller and the fixed support. And that happened because, considering that it's a very old bridge, and there are a significant degradation in stiffness and also structural rotation resistance, so you would expect that this bridge is not really that stable, and there are some decay in those factors. So by moving on to the results and the wind speed boundary conditions, as I told you, so the most effective results after applying the ACE7 design profiles confirm that the accuracy of the results that happen to be from the machine learning and also the modeling part really give a good fit with a very low errors and also very low percentage. It's only less than 10%, it's 9.9%. But also, there are some good results came out from modeling this wind distribution by different factors, and that's the Weibull distribution and also the uniform wind distribution. So both of them really did give some good results, but the uniform wind distribution gave the most convenient and most accurate results. So going forward, by comparing the modeling and also the machine learning, we found out the C1 and C2, which combined the readings of the different strain gauges, and that gave us some good insights about the modeling process and how effective this modeling process and using the machine learning is. So when combining different methods for the experimental and finite element and also the random forest. For the finite element, there are, as I told you, two different ways, uniform and quadrantal wind distributions, which is very important because you don't know really how wind will react in the real case. But for the sake of simplicity, we found out that the uniform wind distribution is the most effective. As you can see on the right side, lower right side, there are different graphs which we obtained from comparing the different finite element methods and also the random forest by using the learning models, which proved our assumption. And even very high ratings in some cases for the intensities of different wind speeds. So as a result of that, as I was saying in the very beginning, when we use the Weibull distribution, we managed to obtain very high occurrences, which was really fitting the real case of the wind distribution and wind intensities, and that's between 40 to 60%, which happened to be very acceptable by the ACE code of wind. And then afterwards, by combining them and doing the analysis for different factors, it happened to be, as I told you, due to different degradation in stiffness and also the resistance and also the asymmetry of the wind distribution, there are some not very consistent results. And that's why we get those different readings. And also in the right side of the slide, we can see different observations with that. As a summary for this, we can say that random forest machine learning process and combining that with the 3D modeling and by using the field real data, we can use a very important element and very important tool and very effective in the cost-wise, instead of just using wind tunnels and very high cost ways to make it real and make it possible to manage and test very old steel bridges and other applications that we can use this machine learning process. We proved that it's very possible with a really low error rates. As we discussed, it's only less than 10%, so it's very acceptable. And then after comparing different wind distributions from the uniform and quadrantal, we managed to get 92% to 86% by comparing the different modeling methods. As I said, uniform wind distributions outperform the quadrantal wind distributions. So it's the real case, as it appears to be, that the uniform wind distributions is the most realistic case which applies to the wind distribution. And then afterwards, as I was saying earlier, that the probabilities of the wind speed, which happen to be between 40% and 60%, confirmed by the ACE code of wind distribution, happen to be a service level range in the service level range, which affected the and caused the displacement of the footings for this old bridge. And as a result, we can say that machine learning can accurately model wind-induced structural responses, offering fast, robust tool for assessing and preserving historic bridges. Here are the references that they used for this study, and thank you.